Hello, my name is Matt Holliday and welcome back to my class on programming in Go. In this section I'm going to get into object-oriented programming, and I'm going to start by talking about methods and interfaces and how they work together in Go. So what are interfaces and methods all about? In my opening segment on object-oriented programming in Go, I talked about abstraction and polymorphism. And what I said was that we wanted to be able to specify abstract behavior and then let concrete objects provide that behavior. And the way we do that in Go is with interfaces and methods. An interface is a specification of abstract behavior. It does it by listing a method set, a number of methods that a concrete object must provide. And of course then we define methods on the concrete types. And if the method set matches properly, then a concrete type can satisfy the interface. And that means it has to have the methods that the interface is asking for. So in the example on the slide, I have thump.stringer, which is an interface in the thump package, and it's been behind the scenes in all of our examples, we just haven't noticed it. And it's satisfied by any object that has a string method. So let's talk about that. Let's switch slides. Okay, what's a method? Well, a method is a special type of function, and that's true in all the object-oriented languages. In a more traditional language where you have classes, you define methods within a class, and there's an invisible parameter on all those methods, which if you reference it inside the method is called self or this or something. And in Go it's just a little different because we don't have classes and we don't define the methods in the class. We define them separately. And so we have a notation that was taken from a language called Oberon 2, where a method is a function that also has a receiver, and the receiver is specified before the function name. So in this example, I have this type inSlice, and the receiver is is, the little is that is an object of type inSlice. Okay, it's an instance of inSlice, and that has a function string, which returns a string. And if I have this function, then I'll be able to use inSlice in a way that produces the output desired. So let's take a look at that. So here's our method, and here's an example program. Okay, so I have part of that program in the playground already. Not all of it. I want to start with this piece of it, right? I have my type inSlice, and what I'm going to say, very important, is in Go, we can put methods on any user-declared type, not just a struct. And so here's an example. I have a method on inSlice, which is a declared type. It's a named type. Underlying type is a slice of int. Okay. So I can create an inSlice variable, and in fact, I can assign to it a slice of int because that's what its underlying type is. I can iterate over it. So I can iterate over my inSlice the same way I could iterate over the base type slice of int. And now I want to print it. And so the question is, what is %v going to print? So let's run it and see. So the loop inside here just printed out each item one at a time, and then I called printf on the whole thing. And what I get is the type of this, it's an inSlice, fine, and it printed out in this particular format. And I did this so it wouldn't look like a regular Go formatted inSlice, right? So I came up here in my little function, I converted the integers to strings, and I printed them out with semicolons between them. Okay, so what does that say? Well, it says that when printf went to print my type with %v, it used my string function. Now, if we looked inside printf or printline or any of these print functions, what we'd see is some interesting logic. The first thing it does is say, is the argument a string? Because if the argument is a string, well, just copy the string to the output. That's easy. And the second thing it does is to check to see if the item is a stringer. Because if it is a stringer, then it can just call the string method, generate the string that way, and put it on the output. It doesn't have to do any more thinking. Right? Now I use this term is-a. Okay? And when we get into object-oriented programming, there's a couple of terms, is-a and has-a. Right? Has-a is about composition. I have something that has something else inside of it, and we'll talk a little bit more about that later. Is-a is more of this substitutability question, okay? And so I'm going to add a variable here that was on the slide. I'm going to add a var s, and I'm going to give it the type thump.stringer, okay? Now, what is the type of s right now? Well, there's two views of that. in the terms of the program right now, the type of S in terms of the text, it's an interface because func.stringer is an interface. So it's an interface variable. And what can I assign to it? Well, I can assign to it anything that satisfies the interface, any actual type that has a string method. And so I can do equals v. I can assign v, where v is my int slice, to a stringer. And if I print that, interestingly enough, I'm going to get the same output. Okay. Now, what's going on here is I said, what is S? Well, from the point of view of the source code, S is a variable of interface type. But at runtime, when I do like a %v to printf, well, what we're really looking at is the type of the thing that the interface is holding on to, right? An interface is it's sort of a reference to abstract behavior that's being satisfied by an actual object, in this case, v, right? And so when I print that, it's really telling me about the type of v, which is the thing that the interface is holding on to. And then, of course, it calls the string method. So I get exactly the same behavior by the second printf that's operating directly on S that I got when I did v, because, as I said, what printf is doing under the covers is if the thing is actually a stringer, then it's using it as a stringer, and it's using the string method. Okay, so but why have interfaces? And here's a good example. If we didn't have interfaces and we didn't have a way to abstract behavior, then we would have a bunch of methods that took different real types, concrete types, like file or buffer or socket or whatever. We'd have to create a different method for each one, and we'd have to know that we're getting a file or a socket and probably do certain things that are special for that. And we don't want to. We want to abstract out the notion of something we can write to. And the answer for that is, in fact, an interface in the I/O package called writer. And it specifies one thing of behavior, and that is that you have a write method. Now, if you look at the write method, it takes a byte slice. And the reason for that is that's the lowest common denominator in a computer, because after all, the computer itself just works with bits and bytes. Okay, it doesn't know about strings or slices. Those are things that are part of the programming language, but they're not part of the actual hardware. So we write the write method in terms of a byte slice, so that anything that provides this method is a writer. And now we can have sort of a generic function, and I'm using generic in quotes. This is not the same as parametric polymorphism with type parameters. That's going to come down the road. All right, but this is also in a sense generic because I can have this function called output2, and what does it take? Well, it takes a writer. In other words, it takes any object that provides a write method that allows me to write bytes to it. So on this slide, I just want to reiterate something I said before, and that is that an interface specifies behavior by a method set. Now, it could be one method, it could be more, and then we have an actual type that implements that method. Now, what you didn't see anywhere is the keyword implements, because it doesn't exist in Go. There are languages that say, hey, if you're going to implement a particular interface, you have to say that when you declare the type. But we're going to talk about this a little later. The way we think about interfaces in Go usually is not from the provider side, but from the consumer side, right? So I'm some piece of function and I need a parameter that provides certain behavior. I, therefore, am the one to say, I want this particular interface with this particular method set to provide this behavior. I, the consumer, okay? And it's up to various providers to provide the right methods. I can therefore have existing objects in a program that have various methods, and I can create a new interface somewhere else that says, hey, I want a subset of those. I just want this one method like write. And that is the behavior that I want as a consumer, and that may be behavior, a specification of behavior that was unknown when those other types were written. Maybe what I've done is actually reduce. So there's already some objects out there, some types that have methods, and there were some interfaces with more than one method. But I say I'm going to create an interface with just one method because I only want to capture that one piece of behavior. Okay? So the way Go does typing is structural in a lot of cases, and that's how we do interfaces in Go. Any type that provides the right methods to satisfy the interface is a member of that interface type in the sense that we're meaning here. We don't say implements, It's automatic. And I'm going to repeat myself on this slide also. I'm just going to reiterate something I said, that we don't have to have a struct in order to have methods. We will see a bunch of examples where we use structs, and there's nothing wrong with that. But I can also create a user-declared type that's not a struct and put methods on it, and we just saw that. And I can even do it with int. I cannot put methods on int, okay? Because I said you can put methods on user-declared types. Int is not, it's a built-in type. And so we're going to see the built-in types of Go, like int and string, don't have methods. There are functions that work on them, they don't have methods. But we can wrap them in another type. So I can create myInt, it's a type of int, and I can add methods to it and do things with it. Now, there may be some requirements for type conversion. If I want to add a regular int and myInt, okay, then we know we're going to have to do a type conversion, but it's not a big deal because the underlying types are still compatible. We can still add integers, even if we have to do a little bit of typecasting. Okay, so Go is very flexible because most languages don't allow you to do this. You can only put methods on what is essentially a struct. And here we can do it on other things. We're going to see that in several examples, and it's going to be quite powerful. Okay, so before I go to the playground and do a little bit more concrete examples in the playground, I want to show one more thing. And that is when we talk about the receiver, there's two kinds of receivers, value receivers and pointer receivers. Now we've already talked about pointer and value semantics, or reference and value semantics. And objects have the same thing. If I have a method that's designed to take a value receiver, then the method gets a copy. So if I look at this method offset, okay, offset takes some x and y values, adds them to the actual receiver, but then it returns a new point. Okay, the receiver, P, is not changed. It can't be changed because it came into this function as a copy. Okay, if I want to change P permanently, so that there's some, I run this method and the original object which is passed into the method is changed, then I need to take a pointer receiver. And that's the case of move. I want to move this point by actually changing its coordinates, right? So I take a pointer receiver and I add this incremental x and y value to the x and y in the point, and the point appears to be at a new place, right, when the method is done. Okay, so now we're going to move on here. I'm going to go to Replit because I want to do some file I/O that I can't do in the playground. And I've got a little program here, which is basically going to do something very simple. I'm going to open one file, copy it to another file that I create. Now, I've eliminated all the error checking just because I don't want that getting in the way of showing you a couple things, right? So this is not good programming style, but we'll do it. And if I run this program, okay, it says copied 30 bytes. And if I go and look at out.text, it exists now. And if I go and do a word count by character on out.text, it says it has 30 characters in it, 30 bytes. Again, we're just doing ASCII, right? So that's my main program. So if I go and look at io.copy, we ask ourselves, what is that? Well, it's a function that takes a couple of interface types. And since they're also in the IO package, we don't see io.writer, we just see writer, because that's how it's defined in the IO package, right? And that's how it works. It reads from a reader and writes to a writer. So if we go and look at, I'm just going to create a temporary local variable here. Right? If I go and look at io.writer, it comes back and says, well, this is going to be, I is going to have the type of this writer interface. It's something that has a method write. And I can do the same thing with reader. Right? The Go doc is a little longer, but if I scroll down in it, it's going to say a reader is an interface with a read method. So anything that has a read method can be the source. Anything with a write method can be the destination. And io.copy is smart enough to do some internal buffering, so it's not just copying one character at a time. But that's not something we need to know about. Right? So can I put something else in this little program? And the answer is I'm going to create something here. All right. We're going to create a new type. All right, the type is byte counter. Now, in fact, byte counter is just going to be another name for an int. All right, I could create a struct with an int inside of it, but I'm not going to do that right now. Again, I want to demonstrate that we can not just tie ourselves up with structs. And I'm going to create a method, write. I may need to collapse this a little bit. All right, and my write method needs to take some sort of byte buffer, and it returns an integer and an error. Okay. And I'm not going to put anything in here right now, but I want to create a new variable down here. All right. Okay, it doesn't really want me to do that. I'm going to create a variable in here because I don't know if it wants me to create a literal like that. So I'm going to create an AND-C. Right, and now I can do that. So I should be able to copy to my byte counter. Okay, so now I got to actually do something. Oh, I know why I didn't call that B before, because I already have a B. All right, so P is this buffer. Now what I'm going to do is I'm going to return the length of it, because what you do in the byte in the write method, you return the number of bytes written in some sense, and of course no error. So in theory this works. I should be able to run this. Okay, but if I run it, it's not going to really do anything. So it's going to tell me something, but it's going to tell me it copied 30 bytes. But actually, if I go down here and print C, it's going to say 0. So I still have to do some work in my byte counter write method. And of course, what I want to do is figure out how many bytes you pass in and add that number of bytes to my actual receiver. Now here's a case where I need a pointer receiver because I want to modify it, right? So every time you pass me some bytes, I'll figure out how long is that number of bytes and I'll put that in here. And if I wanted to, I could make this a little bit cleaner by using a temporary variable. Now, notice also I have to cast whatever that length is, right? So L is an integer. I need to cast it to a byte counter to do the addition to star B, because star B is another byte counter. Okay, so I put a wrapper type around int, if you want to think about it that way. And now whatever ints that I want to add, I've got to cast them. And I'm going to cast it to a byte counter because I'm doing this plus equals function. So now if I run this program, right, I should get 30 both ways. Okay, so my byte counter went up by 30 because that's the number of bytes that were passed into it. And I also returned 30 by being a good citizen, saying, hey, I actually copied the bytes. And so we have this. And I could put those in either order. And my point by saying this, the point of all this is that byte counter is a writer because it has a write method. And so I can put it into io.copy as a destination. It's just as good as any other writer. So I can create, in a sense, a file size counting device, if you will, by opening a file, reading its bytes into my byte counter, and figuring out how many that is. It's not the most efficient way, certainly, but it's a perfectly good example of I have another concrete type byte counter which provides the behavior of a writer, and therefore it is capable of being substituted as a parameter in a function that wants a writer. Now I want to go back to the slides for a second because I want to talk about compatibility among interfaces and concrete types, and I think I can do that easier in a slide. Okay, so if we look at this slide, I've got a couple of variables and they are interfaces, right? W is an io.writer, and RWC is just another one of these things. It has 3 methods, and so it got named read, write, closer. And if you look at it, you're going to find out that it desires 3 things: a read method, a write method, and a close method. Okay, so it's capable of handling a file, right? So if I go look at W, for example, right, I can assign os.standardout to W. Why? Well, os.standardout is actually a file pointer, and files have the write behavior. And we can also assign it down here to RWC, because actually files have the write behavior and the read behavior and the close behavior. Okay? How about a byte buffer? And the answer is, well, I can do that with a byte buffer, Okay, I can assign a byte buffer to W because I can write to a byte buffer. It has read and write methods. But I cannot do that down here. I cannot assign that same buffer to RWC because it only has two of the methods, read and write. It does not have a close method. And so it's not compatible. Okay. And just for grins, I've got one other example. I have time.second. Well, time.second doesn't have any of these methods, so you can't assign it to W or RWC. Okay, fine. So let's assume I've assigned something to W and RWC. How about assigning back and forth between them? And the answer is anything that's an RWC, anything that's a read-write closer, is also a writer because the read-write closer has to have a write method, and the writer interface only wants a write method. So that direction works fine, but the opposite direction fails, okay? The opposite direction fails because anything that's been put into W, what do we know about it? It's a writer. It's something that has a write method. And we cannot assign that to an RWC because we don't know whether it has a read and close method because that's not part of the writer interface, okay? So the assignment in the other direction doesn't work. We can't assign the more restrictive interface to the broader interface. Okay, that's just one of the rules. And it's a good rule, it makes perfect sense. Now the other trick is we talked about pointer and value receivers, and there are a couple of cases, and we'll get into this in more detail later, but there are a couple of cases you got to watch out for. Okay, if something needs a pointer receiver, you can't give it a value that's not addressable. Right? And so I have this type inset, which is actually in the book, and it has a string function, and I want to assign it the string method. And the problem is this doesn't work because I can't call the string method on an inset literal because this construction right here, okay, on the right-hand side of the equal sign is a literal. It's a value that's not really tied anywhere. It doesn't have a place. And if it doesn't have a place, it doesn't have an address. And if it doesn't have an address, we can't have a pointer to it. And therefore, it's impossible to make this call because, in fact, it needs an inset pointer. Now, if we do this, we can do it, right? We create a var s of type inset, and then we call s.string, and that works because now we created a variable, and the variable has a place. Okay? So that works. And then we have this third thing down here, and this is where it gets a little counterintuitive, but right? Fump.stringer represents an object that has a string method. But we define the string method to work on a pointer receiver. So in order to make this assignment work, I have to take the address of S, so I have a pointer to something. I have to have the actual address of the object in order to make fump.stringer happy. All right, and the other way doesn't work. And it doesn't work again because we define the method to take a pointer receiver. And we can only define it one way or the other. So your method either takes a pointer receiver or it takes a value receiver, but you can't overload it and do both. That's not allowed. Okay, so we've talked a little bit about, composition versus inheritance, and we're going to get into composition in the next segment. But I want to talk about composition in a different category, and that is we can also do composition with interfaces. Now, if you look at an interface, right, an interface definition, well, it kind of looks like a struct. It's got curly braces and a list of methods, okay? And we can actually combine them. So I have a reader type, I have a writer type, those are two interfaces. I can define the read-writer interface. Instead of listing out the methods in detail, I can simply say it's the composition of the reader interface with whatever methods it has and the writer interface. Just add them together. Okay, it's a union. Now, it's not a union in the sense of C unions where it's one or the other. This is a both and. Okay, something is a read writer if it's a reader and it's a writer, which means it has a read method and it has a write method. Okay, and so if you looked at anything that's a star file like standard in or standard out, that would work. So why do we do this? Okay, and one of the basic ideas in Go about interfaces is we should keep interfaces small. In fact, in a lot of cases, it's perfectly okay to have these one method interfaces, and then if we need something that has multiple behaviors, we compose them. So we have the plain reader interface and the plain writer interface because a lot of times, and we saw this with io.copy, We just need the one method. Here's another limitation, and that is you have to declare the methods in the same package as the concrete type. And the reason for that is that when Go compiles, it wants to know all the methods for the type all at once. Okay? There are some languages where, and this has been very useful in iOS, with both Swift and Objective-C, you could actually take Apple's standard library classes and add methods to them on the fly in your program. And it's pretty neat. But you also get into dynamic typing, because now you're in a position where your program could have text in it where you try to call a method that you don't really know if it exists or not until you run the program. Interpreted languages are like that also. And in Go, we want static typing. So we want to know what are all the methods that that type has, so we can decide, for example, does it satisfy a particular interface, or is this method call legal? Okay, so we can't extend a type by adding methods in a different package. And the Go compiler will tell you you can't do that. But what we can do is we can extend the type. And I'm previewing composition of structs, okay, which I'm going to talk about in more detail in the next segment. But in a sense, the same way I took the int type and wrapped it by creating the byte counter, I can actually create a struct that embeds another struct, and I can then add a method to it. Now we'll get the same thing. I may have to do some typecasts, because bigger is not a big. Bigger has a big, right? But bigger also has this one more method, all right? And as we'll talk in the next segment, believe it or not, bigger also has whatever methods big had. So now I want to drop back into the playground. I want to work through one more example from the book. I'm going to modify it slightly. It's going to be just a little more complicated. But again, I want to demonstrate some things about methods and interfaces in one more example. So we have the notion of point. We already saw a program. We had a point. So I'm going to create another thing, which is a line. Now, in these cases, these are structs, right? So a point is a struct with x and y. That's its location. And a line, of course, has 2 points, the beginning and the ending. And then I'm going to take a little thing out of the math package and do the calculation of how long is the line. Okay? But I'm going to do it in terms, I'm just going to call it distance. I could have called it length. I'm just going to call it distance. And all it really does is figure out what's the distance between the begin point and the end point. Fine. So far, so good. That's a method, right? It takes a line. It takes a line by value because I'm not going to change the line, so that's perfectly okay. So I'm going to come down here and create a line. Now, in order to create the line, because it has 2 points inside of it, I have to pass it 2 actual point literals. So the keyword point followed by the numbers, that creates the first point, begin, and point again with 4 and 6 for x and y creates the second point. Okay, and those points are required. If I take that out and try to run it, it's going to say, no, you can't do that. Right? I have to actually say, hey, I'm making a point and creating that as one of the values in the line literal, which of course is this thing right here. All of this is the literal that creates the line. Okay, so I have side, and now I can call side.distance, and when I run that, I get 5. Okay, we picked x and y values to come out with nice round numbers. So far so good. We're going to create a new abstraction in this program. All right, in addition to lines, what if I have something that's not a straight line, but it has some lines inside of it? So I'm going to create a path. And we're going to think about, I mean, this could be like a spline, but it's really going to be a bunch of line segments. Right? The path has a bunch of points. So we go from point A to point B to point C. Great. Okay. I can also create a method distance on point. So we're going to come down here, okay, and create a distance method. All right. Now I'm going to name my return just because that's going to make it convenient. If I name my return value, I can use it as a local variable in the program. It's initialized to 0. That's convenient, right? And of course, I'm going to return it. And I could do a naked return. I don't generally like naked returns, so I'm going to return some, even though if I just did return by itself, that would also work. But I'll just go ahead and return some. And so what I need to do now is I need to create or calculate some distances between these points. And I'm going to cheat a little bit. All right. because I don't want to do a whole lot of work. And so what I'm going to do is say, hey, between each 2 points is a line, and I already know how to calculate the distance of a line. So I'm going to do that, right? The sum is going to be accumulating, okay, some line on which I will call distance, all right? Well, what's my line? Well, my line needs a beginning and ending, so it needs the previous point, which I call P, not path, and the current point, right? So if I've got 2 points, right, the distance is from the last point to this point, and then I'll do it again, but now this point will be the last point, which is why I started my for loop at 1, okay? This is another wonderful case of where we could get an off by 1 bug if we started at 0. In fact, we'd crash the program, right? If I start at 1 and I go up to almost the length, and I need a semicolon there, right? So each time I'm saying starting with the second point from the first to the second, and then the third point from the second to the third, until I get to the last point, right? And so I'm just adding up these distances by making a line out of each 2 points and just asking that line for its distance. Now, here's a case where, what is this? This thing right here that I've highlighted in blue is a line literal. It's a value, right? It doesn't have a place. I can't take its address, but that's okay because distance, all right, was defined to take a value receiver. So I can create a value on the fly, calculate its distance, throw the value away. I never stored it in a variable. So it never really had a location, right? And that's fine. So I'm just manufacturing a line very quickly and asking for the distance and throwing it away each time through the loop. This may not be the most efficient way to calculate distance, but that's fine. It works perfectly well, right? It more importantly shows what I want to show. So now I'm going to create an actual path. And I'll try to actually spell it properly. So I'm going to create a path, okay, and it's a path literal. Now, here's the difference. There's an interesting thing going to happen here, and that is because path is actually a slice of points, when I create these points, I will not have to use the point name, okay? I can just create a path, right, and I'll just go from 1, 1 to 5, 1 to 5, 4, back to 1, 1. And again, I'm stealing an example from the book. This is going to be a triangle of some sort. And the reason I'm doing it this way is it'll come out with a nice round number for its length. All right? And so now I can say, you know, perimeter.distance. I don't know why I keep wanting to do that. All right? So again, when my path literal didn't need to say 0.11, 0.51, because it's actually a slice of points, and it just so happens, since we know it's a slice of points, then path knows that everything in it is going to be a point, and we can omit those types. I could write point here, but if I write point there, it's redundant, okay? And possibly a linting tool will say it's redundant, you don't need that. So now I can run the program. I could. I don't know what happened to I got cut out somewhere. Okay, so now I get 2 results. My side, okay, gave me a 5, and now I can calculate the perimeter by just calculating the length of the line segments that I'm manufacturing on the fly, and I get 12. Great. So the perimeter around this triangle, going from one point around the triangle back to the original point, is 12. There's one more thing I want to show about this. Actually, there may be more than one thing. Okay. I'm going to create a method, a function actually, and I'm going to call it print distance. Now, it's a little artificial. I don't think I would create something like this in a real program, but again, I want to make some demonstrations. All right, so I'm going to take something called a distancer, and there's this tendency in Go when we use interfaces to make to take like an adjective and turn it into a noun or something. So a distancer is something that does a distance. A writer is something that does write. Okay, it doesn't always work, but you know, we'll just keep going down that road. So I can have print distance, and now I could, in theory, replace these calls with calls like this. Now I'm missing one thing, and that is I need a definition of distancer. Well, what is distancer? It's an interface with one method, right? Okay. And we're going to define it as the method distance, returning a floating point number. Now, it just so happens that all my things here return nice round numbers that don't have fractional parts. But in fact, in order to do the math, we have to assume that we're doing, squares and square roots and stuff. So we're going to do all these in terms of floats. If I changed one of these numbers just a little bit and run this program, all right, I don't get a round number, but we won't do that. Okay. So now it works, right? Because I have print distance. Print distance wants a distancer, and it calls the distance method on the distancer. And oh, by the way, both side and perimeter are instances of types that satisfy the distancer interface, right? Because a line has a distance and a path has a distance. Okay, so far so good. Now I'm going to play with this a little more. I'm going to do something different here. So I'm going to get rid of paths and distance for the moment. All right. So that was fun while it lasted. We're just going to go back to points and lines. All right. I want to do something else. We're going to have a function that scales the line. Right? In other words, make the distance longer than it is. And it just so happens to make this work. I'm not even going to explain the math. I'm just going to type it here. Okay. To scale this, and we do the same thing for y, we just change all these little things from x to y. That one needs to be capital. All right, so now I have this thing. Right, now I'm just going to run it one more time to make sure we get 5 the way we're supposed to. Okay, so here's the thing. I create this line. Okay, but now we're going to change this because we're going to ask it to make itself twice as long. All right. Unfortunately, this isn't going to work. And again, right, it says it's still a total distance of 5. And why is that? Well, that's because the line took a value receiver. Right. So scale by got a copy of the line, modified the copy, and then at the end of scale by, that copy goes away and the original object didn't change. In order to change it, we have to have a pointer receiver. And now if I run the program, it will just work, and my line will return 10 instead of 5. And if I change the scale to 3, right, now it'll return 15. And I suppose I could do 2.5 and get some fractional number, 12.5, whatever, okay? So we can do that. And this is the important part. Now, there's the other thing, and that is, what if I tried to do this? Let's try this. All right, and the answer is this isn't going to work for a couple of reasons. Okay, the first reason it's not going to work is I can't call the method scale by on this literal. I have this literal line here, okay, and when I call scale by on it, that's a problem because again, scale by now wants a pointer receiver, so I can't do that. Well, that's problem number one. There's actually a second problem, and that is I can't change these methods because scale doesn't return anything. It doesn't return me an object that I could call distance on. But I could have done this a different way. All right. I could do this. And I'll have to do it with 2 points, right? So, Actually, no, I want to keep the begin. The begin didn't change. All right. I want to return a line. All I'm really doing is saying I'm extending the end. So when I scale the line, I'm just moving the end out, right? So I could take a line, change it, return a new line that has been modified. The begin point doesn't change, but I'm giving it a new end point based on this modification here. Okay, great. I could do that. Now when I run the program, I have a typo somewhere. That should be a curly brace. Now, the only trick is, when I call this line right here, it's returning me something that I'm throwing away, and I would need to assign to it. And then if I assign to it and call distance on the assignment, okay, and I scale by 2.5, I get 12.5. We saw that before. And now this other call works because line is a literal. I call a function that takes a value, not a pointer, and it returns a new line, and on that new line I can now call distance. And again, because distance also took a value. So now suddenly I've made this legal. Now, that may or may not be convenient. You may not always want to take a copy of the line, change it, and return it. You may just want to change it in place the way we had it in the original case. And that's a programming decision. That's an engineering decision about how you build your program. Okay, so I've got this one more example in a different playground. And again, I'm taking something out of the book, right? So we have points. That's fine. Point has a distance from another point. All right. Now, in this case, this is different than the line thing. I'm just saying, hey, I have the point function has a distance given another point as a parameter, because we have to have distance between 2 points. And now I'm going to create another type. It's a colored point. And I'm not going to explain again. We're going to talk more about composition, but I'm essentially saying a color point has a point and one more value, one more field, and that is the color. All right. And I can create a colored point by giving it a point and a color. And in this case, I think the color is red, but don't worry about that. So P and Q, P is a point, Q is a colored point. And so the question is, can I take Q and calculate the distance from P? And the answer is yes. Okay. You don't see anything, so I need to actually, and these should be exactly the same, right? Well, again, it would help if I imported FUMPT. Now let's run it. Okay, and we get 2 5s. So the difference from the first point to the second point is the same as from the second point to the first point. That makes logical sense in math. But notice that in the first case, I had to call Q dot distance on P. That's okay. But if I call P dot distance, I had to say Q dot point. And the reason for that is, let's see what happens when I just say pass in Q. And the answer is I can't. Okay? Q is a colored point. It is not a point. I have a point in it, but it is not a point. Okay, so we just did a preview of what's coming up in the next segment, but we're going to talk about composition of structs. There's a bunch of rules, okay, but composition is not inheritance. So a colored point is not a subclass of point, even though it has point stuff in it, and it cannot be substituted. The only thing we can do for substitution is with interfaces, based on behavior, based on methods that these various types define. Okay, so that was the introduction to methods and interfaces, and we walked through a few cases of what's an interface, what's a method, how do they work, and we ended up with this little advanced thing from the next segment that we're about to go into on composition and why composition is not inheritance. We saw a simple example, and now we're going to talk about that in more detail.